In this lecture, we are going to discuss the Euclidean algorithm, which can be used to find the GCD of two numbers. Let us discuss first a theorem, Theorem 3.11. Let a and b be any positive integers and r the remainder when a is divided by b. Then the GCD of a and b is equal to the GCD of b and r. That is, the theorem says that let a and b be any positive integers, and when we divide a by b, the remainder is r. Then the GCD of a and b is equal to GCD of b and the remainder r. So to prove this, let a equal to GCD of a and b and d dash is equal to GCD of b and r. So we have to prove that d equal to d dash. So for this, it is enough to show that d divides d dash and d dash divides d. Now, if we are dividing A by B by division algorithm, there exists a unique quotient Q such that A equal to BQ plus R. First, we are going to show that D divides D dash. So, since D equal to the GCD of A and B, we have D divides A and D divides B. So from this, since D divides B, we have D divides BQ, because we have D divides A and D divides B implies D divides, by theorem 2.4, D divides C1A plus C2B. So if you are taking C1 equals 0 and C2 equal to Q, we get D divides BQ. So now we obtain that D divides A and D divides BQ. Therefore, D divides A minus BQ by using the same theorem. D divides A minus BQ. But from this, we have A minus BQ is equal to R. So, D divides R. This is A minus BQ equal to R from this. So, D divides R. That means D divides B and D divides R. Therefore, D divides GCD of B, R. That is, D divides D dash, because we are taken D dash as GCD of B and R. So D divides D dash. In a similar way, we can prove that D dash divides D also. So we obtain that D divides D dash and D dash divides D. Therefore, we have D equal to D dash. That is, GCD of A comma B is equal to GCD of B and R, because we taken that D equal to GCD of A and B, D dash is equal to GCD of B and R. Now we can discuss an example. Illustrate the above theorem with A equal to 120 and B equal to 28. The previous theorem says that GCD of AB is equal to GCD of B and R, where R is the remainder when A is divided by B. Okay. So here we have A equal to 120 and B equal to 28. So we have to verify the above theorem. We can just verify that the GCD of 120 and 28 is equal to, that is, GCD of AB is equal to 4. You can just verify this. Now by the division algorithm, if you divide 120 by 28, we will get 4 as the quotient and 8 as the remainder. Therefore, by the previous theorem, we have AB equal to the GCD of A and B is equal to GCD of B and R. So here R is equal to 8 and here A equal to 120, B equal to 28. So A comma B is equal to B comma R. So GCD of 120 comma 28 is equal to GCD of 28 comma 8. We know GCD of 28 comma 8 is nothing but 4 itself. So we have verified that the GCD of 120 comma 28 is equal to 4. That is, GCD of A comma B equal to GCD of B comma R, where R is the remainder. Next example, using the above theorem, that is using the theorem 3.11, evaluate the GCD of 2076 and 1776. From the previous theorem, we have GCD of A comma B is equal to GCD of B comma R, where R is the remainder obtained when A is divided by B. So we can take the largest number as A and the smallest number as B. So we can take A equal to 2076 and B equal to 1776. That is, we are dividing A by B. That is, we can take 2076 as the dividend and 1776 as the divisor. So we have, by division algorithm, we have, if you are dividing this 2076 by this 1776, we get 1 as the quotient and remainder will be 300. So we have 2076 is equal to 1 into 1776 plus 300. So by the theorem 3.11 we have GCD of A comma B equal to GCD of B and R. That is, from this we get GCD of 2076 comma 1776 is equal to, this is A and this is B, this is equal to and this is B, this is R, right? This is A, this is B, this is R. So B comma R, that is 1776 comma 300. Now to find this GCD, again we have to apply the division algorithm. That means taking 1776 as the dividend and 300 as the divisor. So we will get 1776 is equal to 5 into 300 plus 276. Therefore, now here we have, this is A and this is B. So we have, this is A, this is B and this is R. So applying this above theorem, we have AB equal to GCD of A comma B is equal to GCD of B and R. So this is equal to GCD of B and R here is 300 comma 276. Now to find this we have to apply again the division algorithm, taking this as A and this as B. Continuing that way, we get the first one is 2076 can be written as 1 into 1776 plus 300. Then again we can express this as, or applying division algorithm, taking this as A and this as B, we get 1776 is equal to 5 into 300 plus 276 as we obtain like this. Now we can express this as A. We have to apply the division algorithm, taking A as 300 and B has the remainder 276. So we have 300 is equal to 1 into 276 plus 24. Now again we have to apply the division algorithm. That is, we have to divide 276 by 24. So 276 is equal to 11 into 24 plus 12. Again we can apply the algorithm, that is taking 24 as the A and 12 as the remainder as the B. That is 24 is equal to 2 into 12 plus 0. This is not 1, this is 0. So we obtained, this is the last non-zero remainder and it will be the GCD of 2076 and 1776. That is, we have the GCD of 2076 1776 is equal to GCD of 1776 comma 300. This is by the theorem 3.11. Now from this we get GCD of 1776 comma 300 is equal to GCD of 300 comma 276, and from this division algorithm we get this GCD of this 300 and 276 is equal to GCD of 276 and 24. So we'll get this, and from this division algorithm we'll get GCD of 276 comma 24 is equal to GCD of 24 and 12, and again we have GCD of 24 and 12 is nothing but 12 itself. That means it will be if you are applying the division algorithm repeatedly, we will get GCD of these numbers will be the last non-zero remainder. The above procedure of finding the GCD of two positive numbers is actually the Euclidean algorithm. We can justify the algorithm. Let A and B be any two positive integers with A greater than or equal to B. A greater than or equal to B. If A equal to B, then the GCD of A and B will be A. So we can assume A is greater than B. So if A greater than B, let R not equal to B. First we are assuming that R not equal to B. Then by the successive application of the division algorithm, we will get a sequence of equations. That is, if you dividing A by B, here we have R naught is the B now. So we will get Q naught as the quotient and R1 as the remainder, where R1 is such that 0 less than or equal to R1 less than R0. This is by division algorithm. Again we can apply the division algorithm for R0 and R1. So that is, R0 can be written as Q1 into R1 plus R2 That is, dividing R0 by R1, we will get Q1 as the quotient and R2 as the remainder, such that R2 is such that 0 less than or equal to R2 less than R1. Again, applying this for R1 and R2, we will get R1 is equal to Q2 R2 plus R3, etc. So continuing like this, we get the following sequence of reminders. Reminders will be, first reminder is B. B is actually we are taken as R0. So R0 is greater than R1, greater than R2, greater than R3, etc. which are greater than or equal to 0. So we know all of these reminders are non-negative and are getting smaller and smaller. Therefore, this sequence should eventually terminate with reminder Rn plus 1 is equal to 0. That means this sequence of reminders are non-negative and getting smaller and smaller. So it will converges to 0. So we will get a reminder Rn plus 1 which will be 0. So in that case, we will get the last two equations in this procedure. We will get this. Here R1 is, we have R0 equal to Q1 R1 plus R2. R1 is equal to Q2 R2 plus R3, so etc. We will get Rn minus 2 is equal to Qn minus 1 Rn minus 1 plus Rn, because here R1 is equal to Q2 R2 R3. That is, Rn minus 2 equal to Qn minus 1 Rn minus 1 plus Rn. And last one will be Rn minus 1 is equal to, this Rn minus 1 is equal to Q1 into Rn plus 0. That is, the next remainder will be 0. Okay, that means Rn plus 1 will be 0. Okay, so these will be the last two equations of this procedure. So it follows that from the previous theorem we have the GCD of a comma b is nothing but GCD of a comma b equal to GCD of a comma r0, and it will be equal to GCD of r0 comma r1, and then it will be equal to GCD of r1 comma r2, etc. And at last we will get that means r0 comma r1 r0 comma r2, etc. This is equal to Rn minus 1 comma Rn. That will be Rn, because we will have Rn minus 1 as greater than Rn, and Rn is a divisor of Rn minus 1. So we have the and it will be the greatest one. So GCD of Rn minus 1 comma Rn is equal to Rn itself. So which is the last non-zero remainder. So this is the Euclidean algorithm. Now we have an example. Apply the Euclidean algorithm to find the GCD of 4076 and 1024. So we have by the successive application of division algorithm, we have 4076. It is the greatest one, so we can take this is as A and this is B. So 4076 is equal to 3 into 1024 plus the remainder will be 104. Again applying for A, taking A equal to 1024. So 1024 equal to 1 into 1004. That is, taking A equal to 1024 and B equal to 1004. We get 1024 is equal to 1 into 1004 plus the remainder will be 20. And the dividend is now we can take as this, that is A equal to 1004 and B equal to 20. And applying the division algorithm, we get 1004 is equal to 50 into 20 plus the remainder will be 4. And again we have 20 is the next one, so this remainder. So taking this as A and this as B, we have 20 equal to 5 into 4 plus 0. So the last non-zero remainder is 4. So the GCD of 4076 comma 1024 is equal to 4. Okay, so we can just apply this Euclidean algorithm to find the GCD of two positive numbers. Next one, a jigsaw puzzle. This puzzle is an application of the Euclidean algorithm to geometry. Suppose we would like to find the GCD of 23, 13. GCD of 23, 13. So by using the Euclidean algorithm, we have 23 can be expressed as 1 into 13 plus the remainder will be 10. And applying the Euclidean algorithm again, 13 and 10. So 13 is equal to 1 into 10 plus 3. The remainder will be 3. And again applying Euclidean algorithm for 10 and 3, we have 10 is equal to 3 into 3 plus 1. And again Euclidean algorithm for 3 and 1, we can write 3 equal to 3 into 1 plus 0. So the last non-zero remainder is 1. Therefore the GCD of 23 comma 13 is equal to 1. Now we can illustrate this procedure geometrically. We found the GCD of 23 and 13. So we can take a rectangle of dimension 23 by 13. That is, we can take a rectangle of length 23 and breadth 13. Now, first we can think of the squares of 13 by 13. That is, from this we can say that in this rectangle we can place only one 13 by 13 rectangle. That is 1 into 13 plus 10. So we can place only one 13 by 13 rectangle. That will be this. This is 23 and this will be 13 and this will be 13. So we can place only one 13 by 13 rectangle. Then the remaining part will be this. Now taking the second equation, 13 is equal to 1 into 10 plus 3. That means in the remaining part we can include only one 10 by 10 rectangle. So let it be this. This is one 10 by 10 rectangle. This is 10 and this length is 10. And the remaining part will be this. So taking third one, we have 10 equal to 3 into 3 plus 1. That means we can include a 3 by 3 rectangles, three numbers. We can include 3 by 3 rectangles, 3 numbers. That is 1, 2, 3. You can include 3 by 3 rectangles, 3 numbers. And the last part is we have only 3. That is 3 equal to 3 into 1 plus 0. That is we can include 1 by 1 rectangles, 3 times. So we have 3 numbers of 1 by 1 rectangles. That is this puzzle. That is called a jigsaw puzzle. So here each divisor d in the algorithm represents the length of the side of a d by d square. And the length of a side of the smallest square will be the GCD, the required GCD. Now we already discussed that the GCD of A and B can be expressed as a linear combination of A and B. That is, we can find alpha and beta such that GCD of A and B is equal to alpha A plus beta B. So for this, here also we can use the Euclidean algorithm. The Euclidean algorithm can be used to express the GCD of A and B as a linear combination of A and B. Okay, so we can discuss it with an example. Using the Euclidean algorithm, express the GCD of 4076, 1024 as a linear combination of 4076 and 1024. So this is actually what we done in the previous example. So from the previous example, by using the Euclidean algorithm, we obtained that the GCD of 4076 and 1024 are equal to 4. These are the equations used in the Euclidean algorithm. So to express this GCD as a linear combination of 4076 and 1024, we have to apply this sequence of equations in the reverse order. That is, from this we have actually the GCD will be 4. So we have to express this 4 as a linear combination of these two numbers. That is, we have to express 4 as a alpha into 4076 plus some beta into 1024. We have to express this 4 as linear combination of these numbers like this. So we have to find alpha and beta. So we know from this we have 4 is equal to the GCD of these numbers. That is, GCD of these two numbers is equal to 4. That is the last non-zero remainder. From this equation we get 4 can be replaced by 1044 minus 50 into 20. That is, from this equation we can replace 4 by this. That is 1004 minus 50 into 20. Now here the previous remainder was 20. Now we can express this 20. Okay, we can express this previous remainder 20 in terms of this. That is, by using this equation we have 20 is equal to 1024 minus 1 into 1004. That is, we have this is equal to 1004 minus 50 into this 20 can be replaced by this. Okay, from this equation. substituting for 20. Again we have 1004 minus 50 into minus 1 into 1004, that is plus 50, that is 51 into, from this we get 51 into 1004 minus 50 into 1024. Now again the previous remainder is 1004, so this can be replaced by 4076 minus 3 into 1024, that is for here this was our previous reminder, so this can be replaced by 4076 minus 3 into 1024 from the first equation. So we have this is equal to 51 into 40. Our numbers are 4076 and 1024. 4076 and 1024. So from this we get 51 into 4076. Now here 1024 into minus 3 into 51 plus minus 50. That is, from this we get 51 into 4076 plus 1024 into here minus 3 into 51, that is minus 153, and here is again minus 50, so minus 50, that is 51 into 4076 minus 203 into 1024. That means we obtained that alpha equal to 51 and beta is equal to minus 2.203. That is, we expressed the GCD of these two numbers as a linear combination of these two numbers. So for this we used the Euclidean algorithm. So if we need to apply that, we have to use the Euclidean algorithm to find the GCD first. Then applying the reverse order, we can express this as a linear combination of the required numbers. Now we have a theorem, Lamest Theorem. The number of divisions needed to compute the GCD of A and B by the Euclidean algorithm is no more than 5 times the number of decimal digits in B, where A greater than or equal to B greater than or equal to 2. Here actually proof is not included in your syllabus. The Lamest theorem says that suppose we are going to find the GCD of A and B by Euclidean algorithm, where A is greater than or equal to B greater than or equal to 2, then number of divisions, that is like this, the number of divisions needed is no more than 5 times the number of decimals in B. That is the Lamest theorem.